Hello, everyone, and thanks for joining me for Micronaut CRaC. CRaC stands for Coordinated Resource at Checkpoint. I will show you the integration that we have in Micronaut Framework during this talk. Who am I? My name is Sergio del Amo. I am a core committer of the Micronaut Framework. I have been involved with the framework since inception. I am currently the development lead in the Micronaut team at the Unity Foundation, which is a non-for-profit organization that hosts the Micronaut Foundation. Hopefully, I will introduce you how exciting the integration that we have with Micronaut CRaC today. So first thing is why. So why what's the problem that CRaC is aiming to solve, basically? So you have heard sometimes that Java is slow, and what people typically means is that Java is slow on a startup. But once a Java application is running, the JVM does a lot of optimization. So it will detect the code paths that you have to optimize, and it will reach a really fast performance level. So Java applications are not slow at all. Java applications are fast, but they require a little bit of time to reach their performance level. So typically, a Java application needs such a RAM to warm up. We typically say that when an application is warm up, we have optimal performance. The problem is that whenever we restart an application, the previous invocation has no record of the optimizations that happened before. So it basically starts from scratch all the time. So if you start an application one time, you will see like the same graph that I showed you before. The second time, you will see the same one. The third time, you will see again the same performance graph, and again and again. So we don't have any record. So the idea of Micronaut CRaC is, what if we could take a snapshot of the application at peak performance and restart from it? So instead of starting from scratch every time, we will start from peak performance, and then we will basically achieve the goal of starting fast from the get-go. So enter CRaC. So CRaC is an OpenJDK project. Is free to use. Is basically being developed and sponsored by Azul, and the synonym is the acronym is Coordinated Resource at Checkpoint. As I said, it's an open source project under OpenJDK, and as the OpenJDK is free to use. And the goals, as I described, are to basically speed up a startup and a warm up. So, and this will allow Java to go in places where it currently may struggle, places such as serverless, places such as container as a service, etc., or Kubernetes clusters with a lot of containers restarts, things like that. So in order to achieve this, CRaC gives us an API. Basically, the goal of the API is to make our applications aware that a checkpoint in CRaC parlance is a snapshot basically being created. So it will make us aware that a checkpoint is about to happen, and it will make us aware that a checkpoint, that basically we are starting in a restore. So we are starting from a checkpoint. And why is this important? It is important because there are some constraints with CRaC. So the constraints that are enforced by CRaC is that at a checkpoint time, you cannot have any open file or sockets. If you have any, the checkpoint will fail. So that's why they give us an API so that we can basically close anything that needs to be closed before the checkpoint. And in the restoration, if we have to essentially restore anything. I think this metaphor is really easy to understand for everyone. At least it's kind of clicks for me. Is we have all have this experience that when we start our laptop from from scratch. It takes a while to boot. But however, when we basically close the lid and open the lid again, the laptop is instantaneously basically a startup. So that's kind of the idea, that instead of starting from scratch, let's start from a restoration point, kind of start from hibernation. The numbers here are not important. I just want to give you like the basically a graphical representation of the orders of magnitude startup improvements that you're going to get with CRaC. So this is a Java application. I think it was a Hello World application run in a Linux laptop that I have here in my office, quite a unpowered Linux laptop. The same application basically being restored from a checkpoint with CRaC, or basically run as a fat job with Java. As you see, orders of magnitude startup improvements. If we want to compare this with a GraalVM native image, you will see that the GraalVM native image is still a little bit faster, but it's the performance gains by CRaC are really comparable to native. So you are going to get a different set of constraints that you will get with GraalVM native images, but it will be basically a different experience to basically create a checkpoint. So both are great solutions in Micronaut to basically achieve the startup gains that you may be looking for. So I created these 4 steps so that you can see what do you need essentially to use CRaC in your Java applications. And I am going to show you in Micronaut Framework. So Micronaut Framework, for those who are coming to this talk who never heard about Micronaut, Micronaut is an open source JVM framework. We allow you to write applications with either Java, Kotlin, or Ruby. Been around since 2018. We released this year Micronaut 4, so it's already quite a mature framework with many people using it in production. And the philosophy of Micronaut is do at build time as much as you can, so that we can have like lean runtimes. And this is kind of really aligned with CRaC, the idea of let's try to do at build time and at checkpoint creation as much as we can, so that basically when we run the application, we run a peak performance. So the first thing is we need a JDK with CRaC, because even CRaC is an OpenJDK project. It's not available in every Java distribution. Fortunately, Azure released already, I think it was back in spring 2023, they released already a distribution of, so if you use for something like SDK man, you can do like SDK list Java, and you will see like some Zulu distributions which have like the CRaC name on it. So if you are on Linux, you will see like Azure already has distributions with CRaC support baked in. So first thing first, we have already JDKs with CRaC, and those are the Azure JDKs. Next step to use CRaC in our projects is we have to add the CRaC dependency to our projects. The CRaC dependency, sorry, is not the io-github.crack, is they changed the name to or CRaC. So that was the old dependency. You will have to add this dependency, which is distributed to Maven Central, to your projects. But when you are using Micronaut, instead of adding this dependency, you will add the Micronaut CRaC dependency. The Micronaut CRaC dependency has a dependency to the or CRaC dependency. So when you are getting when you basically add into your Micronaut projects the Micronaut CRaC dependency, you are getting the other one as well. So really simple, you add the Micronaut CRaC dependency to your project and you are set up. The third thing is, I told you before that CRaC has these constraints that you cannot have any open files or connections before a checkpoint. So we have to write resources to close all of those. And in order to do that, I told you that CRaC gave us an API. This is how the API looks like. Essentially, it's a simple interface with 2 methods. One is before and the other one is after. As you can imagine, CRaC will basically call the before checkpoint just before a checkpoint is taken, and upon restoration, it will call the after restore method. We created an API which combines the previous resource API and the ordered API, which is an API Micronaut, which allows you to basically order bins of a certain type. And that's basically our API, which, as you see, is pretty simple. Is the order resource API, which basically extends from both the CRaC resource API and the Micronaut order API. So how does it look like? In your Micronaut applications, you create a class which implements order resource, and you annotate that class with @singleton. Micronaut will detect that you have bins of type order resource, and it will basically register this in the application context automatically. We have already provided you with several built-in order resource. So the experience that you will get in Micronaut as a developer is that most of the time you are not going to need to create any resource in your applications at all. So for example, we have built-in resource for Netty, for things such as data source resource. Basically, we allow you to use a connection pool such as high-carry in a Micronaut CRaC application. We have resource for Redis, for refreshables bins. I will talk about that more later on. So basically, out of the box, we give you a built-in order resource so that you basically you can forget about that you are using CRaC in your application. As I said, you can nowadays you can have an application that uses Netty, that uses Micronaut Data JDBC, and that uses a high-carry connection pool. In fact, I will show you this in a demo later on. And you don't have to write any code. This works out of the box with Micronaut CRaC. Refreshable scope. So Micronaut as almost any framework that has dependency injection has the concept of scopes. I showed you before that we are using the standard Jakarta.inject singleton annotation to basically tell that a bin is a singleton. We also have another scope which is refreshable, which basically allows the state of a bin to be refreshed either via the refreshed endpoint. If you enable the refreshed endpoint, endpoints in Micronaut are similar to Spring Boot actuators if you are coming from a Spring Boot. And you can also emit a refresh event, and that will essentially do the same as the refresh endpoint. It will basically offload all the refreshable bins. So we sit with basically with an order resource that basically will emit a refresh event before the CRaC checkpoint. What that means is that all refreshable bins will be basically offloaded before a checkpoint. This is a behavior that you can change, but we believe is the right default for CRaC, and that what you will get out of the box. And as I said, if you, for whatever reason, you don't want this behavior, you can turn it off via configuration. The last step that we are missing is register resources in CRaC context. This, when you are using Micronaut CRaC, is incredibly easy because basically Micronaut will register the bins of type order resource automatically in the CRaC context for you. And it's important that the order resource extends the order interface because Micronaut will use the order that you define to register bins. So to register these resources in the CRaC context, because essentially the order that you register the resources in the CRaC context is the reversed order that they will be restored. So you can essentially control how you want your bins to be invoked upon restoration with the order. So really easy. JDK with CRaC enabled, that will be a tool. The Micronaut CRaC dependency, you write resources, and you register the resources in the CRaC context, which Micronaut does automatically for you. More constraints. CRaC is basically based on a feature on the Linux operating system. So it's not available neither in Windows or Mac OS. So this is a Linux-only technology. Initially, it was only available in x86 architecture. I think it's now available also in ARM, but not 100% sure. So initially, it was only x86 as well. To work around this, so myself and my colleague Tim Yates, who did most of the work on Micronaut CRaC, we work both on macOS. So we wrote an API that you will typically use in your test, which we named the checkpoint simulator, which basically allows you to emulate a checkpoint programmatically. So as you see in this test, I am using the checkpoint simulator to run before checkpoint, and then I am stopping the server manually, and then I am running a run after restart and starting the server manually. So this essentially will allow you to emulate in your test that your application will behave correctly in when you take actually a real checkpoint of your application. So I will show you this later in a demo project, but that's pretty useful, and we use it a lot. Micronaut by default loads singletons lazily, but in CRaC, you typically want to take the checkpoint when your application is in peak performance. So ideally, you want to start your application, initialize everything, warm it up with enough load so that the JDK can do all the optimizations, and then checkpoint it. So when you go to Micronaut Launch, which is our website to generate Micronaut applications, and you select the CRaC feature, you will see that your application class has this code, which basically will initialize eagerly all the singletons in your application. So whenever you are using CRaC, we recommend you that you basically eagerly initialize singletons. It will require root privilege when running via Docker. I will show you more. I think this is something that Sul is working to basically get rid of this constraint, but this is another constraint as well that you are going to face. So how does it work? How can I generate a checkpoint? So this is basically what you will do. You will run your application as you will normally do. So here I am running a fat jar of a Micronaut application. And you will use the flag CRaC checkpoint 2, and you will supply a folder. And then in another terminal, you can use the J command to essentially checkpoint the application, and that will generate the checkpoint in that folder above. So here I am checkpointing to in a folder called home Ubuntu CRaC files. And this is how you will basically create a checkpoint via the terminal. And how will you restore from a checkpoint? So instead of starting with Java -jar, you will do something like Java -exec CRaC restore from, and you will point to the folder where you have your checkpoint files, and this will essentially start from a checkpoint. In order to make this a little bit more easy, we baked the ability to basically create a checkpoint inside a Docker image and start from the checkpoint inside our build tool. So Micronaut supports both Gradle and Maven. We have both Gradle plugins and Maven plugins for both build tools. And in Gradle, we have a task called Docker build CRaC, and the equivalent in Maven will be Maven packaging Docker, Docker CRaC. And what this will do, so inside the Docker image, it will download the Azul JDK with CRaC. It will run the application. It will run a warm-up script that you can provide. By default, the warm-up script that we have is basically, I think, a curl command against the root of the application, but you can create a warm-up script custom to your needs. and then we will checkpoint, and then the entry point of the Docker image will be the checkpointed application, basically. So I will show you in a demo that you will see that this will basically give you like immense orders of magnitude startup improvements. What are the use cases that I see for Micronaut CRaC? So one is, for example, deploying to a container as a service solution such as Cloud Run or Fargate. We have a Micronaut guide, which is linked below, which shows how to deploy a CRaC container image to Google Cloud Run. And you will see that you get really great startup improvements in Google Cloud Run. Another use of CRaC is AWS Lambda SnapStart, which was announced earlier this year, or late December, maybe. So this basically, SnapStart supports the same CRaC API. So if you are using Micronaut CRaC in Lambda, this will work out of the box. Even if SnapStart is behind the scenes, is not using the Azure JDK, basically it's the same concept. They will basically create a checkpoint or a snapshot, they call it, and they will call basically the CRaC API. So Micronaut CRaC and Lambda are a perfect fit, and you will get like amazing as well startup improvements with a Java runtime plus SnapStart. So I'm going to show you a demo before leaving some time for questions. So I have here a Micronaut application. Let me show it to you. A pretty simple application. I have an application.java class with beans, with singletons eagerly initialized. I have a hello world controller, which returns a JSON object with a key of message and the value hello world. Micronaut by default answers JSON. So if you don't see any media type annotations here, that's why. So this will be basically when I run my application, by default will start the localhost 8080, and this will be the root of my application. I have, again, a login resource. This is how you will write resources. As you see, I don't need to write resources for my application because Micronaut already ships with built-in resources. And then I have here another controller, which basically shows the reversible scope. I am basically, upon the controller constructor, I am basically taking the date. And I have a test that basically shows that the date changes after the checkpoint. Let me show you that test. So I am using here the API that I told you before, the checkpoint simulator. So I am starting a server with the resources block in Java. I am getting the checkpoint simulator. I am checking that the date in the controller basically remains the same. And then I am running the before checkpoint. I am stopping the server, running the after restore, starting the server, and the date has changed because the time controller was annotated with an add refreshable. I have the same test for the hello world controller. I am basically testing here that I have this utility class which will run this method before the checkpoint and after the checkpoint. I am essentially checking that the application returns hello world in both cases. So this is basically showing that we can start and stop the native server without problems. I have a test which basically verifies that things are eagerly initialized, the singletons. And the last interesting test that I have here for you is a CRaC can contribute to the info endpoint, and it will basically add like an entry to the info endpoint response, giving you the restoration type and the uptime since restoration. So this is, if you want to have your info endpoint in production, you can get this information as well. I want to show you, in order to show you startup times, I have this bash script, which I'm going to show you. which I'm going to show you here. So I have this pass script, which I will be invoking. I wanted to show you first. So it's basically allows you to, it's a really simple script which will start an application. It will start either via a fat jar, a Docker image, a native executable, or from a checkpoint inclusive. And it will basically, what it does, it starts the application. It does a curl request against localhost 8080, so basically to the root of the application, and it basically will measure. So this is basically a script to measure time to first request, and it will allow it to compare different scenarios. So I have here the project. I'm gonna do a Gradle build. I think I did it before. This is executing the test with a 5-second sleep in the eagerly initialized test. So this is basically what I'm gonna do is I'm gonna do this fat jar, right? And I'm gonna do so you see the startup time is 400 milliseconds, and I could do here localhost 8080, and this will return hello world. So far so good. If I run my bash script for this, so if I could take here users GitHub del Amo CRaC demo build libs. So if I run my time to first request script for this fat jar, this was let me run it again so we can see it. Oh, it's cleaning up. So you may not see it well, but it's telling me like a little bit like 673 milliseconds, 657 milliseconds, 670 milliseconds. Let me show you Docker running. And I have Postgres running because I want to show you like a Postgres demo later on, but I don't have like my CRaC demo. So I'm gonna run here. I'm gonna run Docker build. So this will be like the normal Docker image of my application, no CRaC involved. I'm gonna build like an image for my application. And you see this was tagged with CRaC demo latest. I'm gonna take this and I'm gonna run it here with my time to first request. And this is gonna be time to first request. I think I have to do -D for Docker. And this was pretty much the same as the fat jar, a little bit more sometimes, but it's like between 650 milliseconds and 700 milliseconds. This is a really powerful computer, by the way. And now we are gonna run, instead of that, we are gonna do the Docker image with Docker build CRaC. So this will essentially, it will download the Azul JDK, it will run the application inside it, it will checkpoint it, and it will run a warm-up script that you are seeing here. So let's see if this works correctly. Let me try to run the script now. Hopefully this works. So you see the startup improvements went from between 650 to 700 milliseconds to more or less between 100 and 150 milliseconds. So quite a significant startup improvements with the same code, just by using Docker build CRaC. So as you see, pretty huge startup improvements. I wanted to show you another demo, which is the same application, but with instead of just hello world, something not really terribly complex, but more complex. So I have the same application, but now I have Micronaut data JDBC. I have Micronaut data JDBC with a high carry connection pool and a Postgres database. I have an entity. This will be basically like if you're coming from JPA, like an entity, similar to that, but with Microdata JDBC, you will use the mapped entity. Annotation, I have like a primary key, which will be a long and a message, nothing that you have not seen before. I have, with Microdata JDBC, you will use the repository pattern. So I have here like an interface, which Microdata JDBC will generate an implementation for me at build time. I am extending from the CRaC repository. So this CRaC repository will give me methods such as find all, find by, delete all, delete by, etc. And in my hello world controller now, instead of responding just hello world, what I am doing is I am doing constructor injection of the message repository, and I am essentially getting all the messages and essentially responding the first one as a map. So the same response, and then I have a startup listener we will save a message in the database. Upon application startup is the database is basically empty. So if I am using here, I have here my connection configuration. One thing that you will need to use Micronaut CRaC with Hikari is you will have to allow pull suspension. So this is in our Micronaut documentation, in the Micronaut CRaC documentation, and you will see it. If you don't have this setting in your application, you will see like a startup error which hinting you to use that. And here in application dev, basically I have like my application by default will start in the development environment. That will use this configuration that I have to essentially use the database that is currently running in Docker. And I have it this JDBC URL so that my application that is going to be running in a Docker image can basically connect to the database that is running in the other Docker image. So with this in place, I'm going to do Docker build again. And I'm going to try to run the time to first request script. And this took almost 1 second. So this thing is like connecting to a real database, checking up on startup that the application is empty, etc. So this takes almost 1 second. And now we're gonna do the same thing, but with CRaC. And what this demo is showing to you is that you can use the Netty, you can use Microdata JDBC, Hikari out of the box with CRaC without doing anything, basically. We do all of it for it. So let's see where we are with CRaC. So we are still around 100 milliseconds. Now it took almost 200 milliseconds, 100 milliseconds more or less. So as you see, even with a database, the startup improvements is quite amazing, the improvement that you get. So it's like 1 second versus 100 milliseconds. And yeah, the demo is in my repo. You will see there is like a branch for Hikari and a branch without the database. I wanted to leave some minutes for questions. So these are the some resources to learn more about CRaC, including links to Micronaut guides and links to the Azul documentation. So I don't know if there are any questions, but yeah, thank you.